type problem I want to look at right here is what I have dubbed a rate in, rate out problem. This is not the official name of it, but these are the problems where you are given a rate that something grows and the rate that that same thing shrinks or goes in or goes out or increases or decreases. And it's how to use both of those functions in conjunction. Hey, that rhymed. To answer larger questions. And then we're going to look at an actual AP problem from 2005 which uses this type thought process. So in these problems, you are given the rate that something increases and the rate that that exact same thing decreases. So here, if something is increasing, I'm going to call that the rate in. The rate that something decreases is what I'm dubbing the rate out. Your total change is always going to be your rate in minus rate out. So that's going to be your rate in minus the rate out. If the problem does not predefine your functions for you, like we'll be given f and g, but I'm also going to come up with a third function, which I will call a of t, not a prime, but a of t, which I'm going to let that be the function that actually represents the total amount at time t. So if a is the total amount, my total change is going to be a prime of t, and the total change will always be the rate in minus the rate out, which in this case would be f of t minus g of t. So rate in minus rate out is always going to be your total amount change. And then the total amount, well, if I want the actual amount, I'm going to have to do the antiderivative of the rate. So I'm aware that the antiderivative of f of t minus g of t is going to be needed. However, in these problems, you're going to be given some initial condition. I probably should have included that in here. Given some initial condition. And usually it's centered at, or starting at time t equals 0. Every now and then they'll give you a condition like the amount at time 4 is 27. I don't know. And so you'd have to center things at 4. But if I want my amount at time t, well, that would be a of t. And what I need to include here is we're actually going to start with my initial condition, and then we'll measure the rate of change from that initial point, which I'm using 0 here, to some unknown t value here. So if I want the amount at time 3, then I'll do a of 0 plus the area from 0 to 3. Time at 5 would be plus the area from 0 to 5. Now I do have a slight problem here, because I have a t in my limit of integration as well as t's in my limit, or in my integral, and you're not allowed to have the same variable. I'm not going to flesh that out in great detail here, but just trust me on that one. So what I'm going to do is I'm going to change these to just some other variable, and x is usually the standard choice. So that's going to be the function used to get the total amount at time t. And these are usually calculator active problems because they tend to get ugly with the integration, although sometimes they're not, whatever. All right, so let's look at an actual problem. This is from 2005, the AP Calculus AB exam. I don't think this was on the BC test this year. This is a calculator active problem. So the first thing I would do the second I read this problem is I would go to my calculator and plug these functions in. And there you can see that I have already graphed these equations. I don't really care what the graph looks like right now. I just wanted to go ahead and have these stored. So I have my rate out, which I think was the top one, is F1, and the rate in is F2. So going back and looking at the problem, the context of the problem, I guess I put these in the calculator too soon. I hadn't even read the problem yet. What we have here is a beach, and the water or the ocean is removing sand from the beach at this rate, and at the same time a pumping station is adding sand at this rate. So what we have here, this is going to be my rate out. That's the rate that sand is being removed, and a pumping station is adding sand at this rate. I have plugged these in, and let me look at my calculator again. I think the top function is my F1. So F1 is 2 plus 5 sine. Whoops, and there we go. And yeah, so this, I'm also going to make a note that this is my F1 and this is my F2. Always make note of how things are entered in your calculator so you don't mess up later. Let's see, continuing on. R and T have the same units. Cubic yards per hour, T is measured in hours. Always pay attention to units. The next piece of information is important. At time T equals 0, the beach contains 2,500 cubic yards of sand. There is your initial condition. Now they have not yet defined the function for the total amount of sand, so I'm going to go with my standard A of t. So I'm going to let A of t equal the amount of sand, the actual amount, not the rate that is changing, but the amount of sand at time t. And the initial condition they've given us is that A of 0 is equal to 2,500. Also, since I know that the rate's in and the rate's out, I'm going to go ahead and define my derivative of A of t. A prime of t is going to be my rate in, which is S of t, minus my rate out, which is R of t. And so all of that is good information to go ahead and make note of and define and have it ready to go, because you're almost always going to use those three pieces of information. So continuing on, how much sand will the tide remove during the 6-hour period? It does tell you to indicate units of measure, but they shouldn't have to tell you that. You should do that automatically. So we are looking strictly at the amount of sand being removed, which is my top function. And so this would be the area from 0 to 6 under the function R of t. Since they defined it R of t, you are actually free to use that notation in your work shown. Just remember that even though it is a calculator problem and you could throw this in the calculator and get your answer with no work shown, the setup is usually worth just as much, if not more, than the actual answer. So always make sure you write your integral complete with the dt. You can't forget that part. And there's your answer when you throw it in the calculator. So we get 31.8159. Now remember, on the AP exam you have to be accurate to the third decimal, so you could follow standard rounding procedures, 31.816, or you could use a method called truncating, which is 31.8.5, which means you just quit writing after the third decimal. The units of measure, amount of sand is being measured in cubic yards, so this would be in yards cubed, and that would be your answer for number 8. Remember to always show your setup. Okay, this information right here is going to be very important, so I'm going to continue copying and pasting this on over. Let's look at question B. All right, write an expression y of t for the total number of cubic yards on the beach. Okay, now this is that question that I mentioned in one of the first slides. However, they have defined the function as y. I've been calling it a, so I'm going to take a second to change my a's to y's. There we go. And let's see, we want an expression for y of t, the actual amount of sand on the beach at time t. Well, here we're going to start with our initial condition. We know that y of 0 is 2,500, so I'm going to start with y of 0, and then we're going to measure the change, which was S of t minus R of t. Now remember, you're not allowed to have the same variable, so I'm going to go ahead and call this S of x minus R of x. And we want to measure that change from 0, which was my initial time, up to some unknown t value. And that's all there is to do with part B. Actually I shouldn't say that's all there is. Since we know that y of 0 is 2,500, let's go ahead and plug in 2,500 for the y of 0. And now we're done. 0 to t under S of x minus R of x. So there's your answer for y of t. You can pretty much guarantee that's going to be used later on in the problem. Okay, so there's R of t. Moving on to part C. Find the rate at which the total amount of sand is changing at time 4. Now here we want the rate at which the total amount is changing. The rate at which the total amount of changing is going to be y prime, and they're asking specifically at 4, so y prime of 4 is what? And here's where it helps to have made those notes at the beginning of the problem where I defined my function. That's still a's. I forgot to recopy with the y's. Hold on. There we go. So here's where it's helpful to have made these notes from the beginning of the problem, because I already have my y prime function defined. So y prime of 4, I'm simply going to plug 4 in here. So that would be S of 4 minus R of 4. Always write down your setup, which I'm plugging into S minus R, and then we'll go in the calculator to get that answer. All right, and there's our answer, negative 1.90. This is another one where you could round it, or you could truncate it, negative 1.908. Now, they did not stress or tell you to include units, but you always include units. Our rate of change for this problem is the amount per unit time. My amount is measured in yards cubed. and my unit of time is measured in hours, always make, whoa, not natural logs, hours. So always include your units. And something they did not do for this problem, but they do this very frequently, is ask you to interpret that answer in the context of the problem. So in this case, what this means, my rate of change at time 4 is negative 1.9. That simply means the amount of sand on the beach is decreasing at this rate. And so if it asks you to interpret your answer, you just have to write out a sentence saying the amount of sand on the beach is decreasing at a rate of 1.909 cubic yards per hour. Something, I don't know. All right, last one, part B. Now let me copy this so I can move it over as well. All right, from 0 to 6, at what time is the amount of sand on the beach a minimum? And anytime you are asked for a minimum, you can guarantee you're going to need critical numbers. In calculus, you're almost always going to need critical numbers for the minimum. Now, this one's also on a closed interval, so this one is actually going to be an extreme value theorem question, which makes it a little bit easier. And anytime there's an extreme value theorem question, you need to go ahead and indicate what your candidates are, where you can possibly have an absolute minimum. Candidates are your endpoints, which in this case are when t equals 0 and t equals 6. And my critical numbers. So I'm going to find my critical numbers by setting the derivative, which is y prime of t, equal to 0. So y prime, which is s of t minus r of t, needs to equal 0. That's going to happen whenever my rate in is equal to the rate out. And I'm going to solve that on the calculator. Just remember, anytime you solve an equation on the calculator, you must write down what the equation is. And in this case, I'm solving s of t equals r of t. On the calculator, that is going to be when the two graphs intersect each other. So I'm going to go menu, analyze, intersect. And so I have an intersection at 5.1179, and I will store that answer. So click, control, store. I'm going to store that answer for A because you will almost always need to use that answer. Even if you don't need to use it, it only takes a second to store it. So always make sure you store your answers just in case you need them later. So that was, geez, now I done forgot what it was. 5.1 something, something, something. Where is it? 117. So 5.117 is the other critical number, which I'm going to store in my calculator for A. Now, to know at which of those three times, 0, 6, or 5.117, the amount of sand is a minimum, I'm going to plug those three back into the original function. So I'm going to find my amount at time 0. I'm going to find my amount at the critical number of 5.117. And I'm going to find the amount at the other endpoint of 6. And the way we find those amounts is we go back to the function we came up with in part B, and we plug in our numbers. Now, 0 was given. We know the initial amount was 2,500, so we don't have to plug that one in. But I do need to plug in 5.117 and 6, so let's plug those in the calculator. All right, and there are the values for those 2 points in time. So that's at my time A, that was 2492.369, and remember, you do need to be accurate to the third decimal unless otherwise specified. And 2493.27. And here's another one where you could round. Of course, in this case, it doesn't matter because it's not the minimum. I'll just write 276. And since we're looking for the minimum occurs at the critical number of 5.117. And it does also ask you what the minimum value is. So in this case, the minimum amount of sand. So the minimum amount of sand is 2,492.369. Always include proper units, yards cubed, at time t equals 5.117 hours. Always make sure you include units. So there's our answer. It does ask you to justify your answer. In extreme value theorem questions, we're on the closed interval. When you show that you've considered the endpoints, when you've found the critical number, and you have shown the comparison of the three values or however many you have, the work shown is your justification. You don't have to go through with some conclusive statement now. Now, had you chosen to go through the first derivative test, where you consider intervals to the left of your critical number and the right of the critical number and all of that, then you would need to go through a little bit more justification. And that's why I said a few minutes ago that extreme value theorem actually makes it a little bit easier, because you know where your candidates are and you simply plug into the function to evaluate. So there you go. That's what I dub a rate in, rate out problem. These have been increasingly popular in recent years on the AP exam, so I wanted to flush one out for you.